இல்லைங்க ஃபர்ஸ்ட் ஸ்லைடு டைட்டில் போட்டு வை. இதெல்லாம் தேவையில்லாம போட்டு வைக்காத ஸ்கிரீன் எல்லாம். ஃபர்ஸ்ட் ஸ்லைடு போடு. ஃபர்ஸ்ட் ஸ்லைடு போடுமா. இந்த இதெல்லாம் ஸ்கிரீன்லாம் வேண்டாம். ஃபர்ஸ்ட் ஸ்லைடு போடுமா. டைட்டில் போடுப்பா. அப்படியே இருக்கும். Sir, good afternoon, sir. Good afternoon, sir. Muted, sir. Yours.
Okay. Can you hear me now?
No, I can hear you.
Okay.
I'm just calling Sagu actually. You will be joining. Hello. Silambaran.
Yes, sir.
We can start now. Wait 2 minutes. I'm starting.
So can I start?
You can start. You can start. Silambaran.
Okay, sir. Very good afternoon, sir. Myself, Salambaran. My thesis title is Transition Metal Based Heteroatom Doped Carbon Composites for High Performance Supercapacitors.
Sir, audible, sir?
Sir, can you hear me? Hello. Hello, sir.
Maiyalagan, I am hearing.
Okay, sir. Okay, sir. Thanks.
You go ahead.
Okay, sir. So this is my academic detail. My professional registration 10/12/2019. My first DC meeting 13/1/2020. My comprehensive Viva meeting 27/9/2021. And my pre-PhD Viva for 24/2023. An overview of thesis, chapter 1, introduction, chapter 2, experimental methods and techniques, and chapter 3, nitrogen doped porous carbon coated on MnCO2O4 nanospheres as electrode materials for high performance asymmetric supercapacitor. Chapter 4, nickel doped cobalt oxide spindle nanospheres embedded with nitrogen doped carbon composites derived from bimetallic nickel cobalt metal organic framework as high performance asymmetric supercapacitor. Chapter 5, enhanced electrochemical performance of cobalt doped MOS2 NSRGO composite as electrode materials for supercapacitor application. Chapter 6, nanoflower nickel cobalt LTH nanosheets coupled with the NSRGO composite as electrode materials for high performance asymmetric supercapacitor application. Chapter 7, conclusions and future work. So, chapter 1. So nowadays, it's many of environmental pollution and energy shortages there because due to the development of economy and to increasing the population. At the same time, other energy like conventional energies, so like fossil fuel and coal and gas like that is there. But this energy have some drawback. For global warming and air pollution, then other energy for renewable energy, for solar and steam and wind energy, but this energy also have some drawback, for high cost and season dependent energy, and compared to the electrochemical energy storage system to overcome all those problems. Next to the energy storage devices, here I am just showed to the energy density versus power density to compare to other energy storage system in a supercapacitor for a Ragan plot. In energy density compared to the battery, the supercapacitor for less for 1 to 10, but the power density the compared to battery, the supercapacitor was more for 500 to for 10,000. And the charge and discharge time within 7 to 2 minutes happen to the supercapacitor, but the battery it will take on for hour basis. Then the Coulombic efficiency for 85 to 98% for supercapacitor. Then the cyclic stability for the less than 500 cycle for supercapacitor, and compared to battery, the supercapacitor for cycle stability for very more cycle stability have. Next, the supercapacitor means the two electrode to separated by separator to immersed into the electrolyte. Then the electrostatic force to create the charge and due to the polarization of electrolyte. Next, the classification of supercapacitor. The supercapacitor have three type of classification. One is the electrical double layer capacitor, one is the pseudo capacitor, and another one is the hybrid capacitors. Next, the relationship between different energy storage mechanism. In energy storage mechanism, to anion and cation and to interface of an electrode and electrolyte. This have to the fundamental of an electrochemistry. In the basis, the electrical double layer capacitor they have the adjustments of cation and anion to the interface of electrode and electrolyte. Then, for example, for the nanocarbon, the CV structure for structure nature for the rectangular box type. Then the charge discharge for symmetrical triangular planar. Then the pseudocapacitor have the three type of reaction mechanism. So this one is the surface redox mechanism. Another one is the intercalation pseudocapacitor. Another one is for battery type and Faraday reaction. In CV structure for quasi rectangular box type, then the charge discharge structure for the quasi triangular planar. Next, the requirement of electrode material for supercapacitors. The requirement for we want to choose the low cost material and easy fabrication process and high electrochemical reactivity and fast redox reaction and high electrical conductivity. It will give to the more power density and high surface area. It will give to for more energy density and less than energy density have more specific capacitance and less than power density to improve the high rate capability. Next, the strategy to enhance the performance of supercapacitor. The strategy for a nanostructure, it will give to the large surface area and more active site and short ionic diffusion path. Then the composite, it will give to the good conductivity and enhance the structural stability. This is all the strategy to improve the electrochemical performance of supercapacitor. Next, the motivation. The transition metal oxide, it will give to the variable oxidation state and increasing the specific capacitance and less cost and environmental friendly. At the same time, the electronic conductivity for less and charge storage efficiency also less. Then after that heteroatom doped carbon to composite to the transition metal oxide automatically to improve the electronic conductivity and charge storage efficiency and cyclic stability and rate capability. And in the basis, the chapter 3, we prepared to the MnCO2O4 at nitrogen doped carbon, and chapter 4, nickel doped cobalt oxide, nitrogen doped carbon sphere. Chapter 5, the cobalt doped MOS2 composite to the NSRGO. Chapter 6, nickel cobalt LDH composite to the NSRGO. Next one, the objectives. The development of advanced transition metal oxide with heteroatom doped carbon to composite to improve the electrochemical performance and design the nano composite material like transition metal oxide and nitrogen doped carbon to improve the high performance of supercapacitor. Then the crystal structure and phase purity to investigate on for XRD. Next, the morphological study to prepared by the SEM and TEM analysis. Then the CV and GCD and impedance to evaluate by the electrochemical performance. Then energy density and power density to optimize on asymmetric supercapacitor and aqueous electrolyte. Next, the chapter 2, the experimental methods and techniques. In chemical and solvent to be used to the commercially and without any further purification. The physical characterization we took on XRD and XPS and SCM. TEM and BET and MRS. Then the electrochemical measurement for an cyclic voltammetry, the chronopotentiometry and electrochemical impedance spectroscopy and two electrode system. Next, the electrode fabrication. The electrode fabrication, our prepared activated material, then carbon block and PVDF, all these three material to make the 8:10:10 ratio. After that, for using the solvent for NMP, then to mortar for 1 hour. Then before the nickel foam 1.5 into 0.5 centimeter square, just cut it and clean to cut, and then we dried for 1 hour. After that, the slurry to coat it on the for 1 into 1 area for surface. Then to dry on 12 hours. Finally, to measure the SP300 potentiostat and galvanostat. The experimental condition we used to the for an electrolyte for 1 mole KOH and 1 mole sodium sulfate and working electrode for nickel foam, reference electrode for mercury and mercury oxide, counter electrode for platinum wire. Next, the techniques and formula. The specific capacitance for using the formula for I into del T divided by M into del V. The next, the surface capacitive controlled and diffusion controlled process for to calculated by the power law. So I is equal to AV power B. Then the Coulombic efficiency for epsilon R is equal to T, the discharge time divided by charge time into 100. Next, the two electrode system, the mass loading to balancing by the m plus divided by m minus is equal to the specific capacitance of anion into del v square del v minus then the specific capacitance of the cation into del v plus. Then the energy density for using the formula for specific capacitance into del v squared divided by 3.6. The power density for use for an energy density into 3600 divided by del T. Next, the chapter 3, the nitrogen doped porous carbon to coated on Mn CO2O4 nanospace as electrode material for high performance asymmetric supercapacitors. In synthesis procedure, here we prepared by the solvothermal method for using the precursors manganese and cobalt to 1:2 ratio we taken. Then after that, for using the solvent for ethylene glycol, then to make the 200 degrees C for 20 hours. Then finally, that prepared material to make the annealing test to 600 degrees C for 10 hours. Then we got for Mn CO2O4 porous sphere. Then that after that to dopamine composite to 3 variation we prepared to like 1:1 ratio and 1:2 ratio and 2:1 ratio. Then the prepared material to carbonization to the 800 degrees C for 3 hours, and finally we got the coarser structure like MnCO2O4 at nitrogen doped carbon. In XRD analysis, in MnCO2O4, the 2 theta range for around 35.6. Then the plane is 311, and compared to nitrogen doped carbon composite 1 and composite 2 and composite 3. The slightly the peak intensity to decreasing and slightly to negligible to shift is there. But here that carbon peak is not showed here because the carbon peak have to the amorphous nature. Then after that, the figure B is the NSRGO for XRD pattern for around 25 for 2 theta value. The plane is 002. This NSRGO we use to the for negative electrode device. Next, the BET analysis for MnCO2O4, the surface area for 72, and then after that composite material for 25. Next, the morphological analysis for FESM. Figure A is the MnCO2O4 for rug surface of an MnCO2O4 porous sphere. Then figure B is the composite of nitrogen doped carbon for the SEM analysis. So compared to figure A, figure B have the smooth surface because the coated on nitrogen doped carbon to the surface. Then after that, figure C is the for pure MnCO2O4 for TEM analysis. For one more time, we uniformly to conform to the porous structure. Then figure D is the to conform to the core cell structure for inner layer of MnCO2O4 for outer layer for outer cell for nitrogen doped carbon. Then figure E is the for Springer's calculation, the D spacing for 0.9 nanometer. The plane is 311. Figure F is the SID pattern. Next, the XPS spectroscopy of MnCO2O4 at nitrogen doped carbon. Figure A is the in that XPS we conform to the for elemental and valence state and the composition. So the figure A is this the survey spectroscopy. The global 2p and manganese and oxygen, nitrogen and carbon, all this element we conform to the XPS analysis to survey spectroscopy. Figure B is the global 2p for +2 and +3 oxidation state have. Then manganese 2p to conform for 2+ and 3+ oxidation state. Then carbon 1s to all this carbon to nitrogen and carbon to oxygen bond and carbon to carbon to all this carbon to conformed here. Then nitrogen, pyridinic nitrogen, pyrrolic nitrogen, oxide nitrogen, all this nitrogen to conform to the in figure E. Then the oxygen 1s for to conform to the metal to oxygen, all this oxygens to conform to the figure F. Next one, the electrochemical studies for CV, cyclic voltammetry. In cyclic voltammetry, we took on for around -0.12 for 0.55 for potential. The scan rate for up to for 5 millivolt per second to 100 millivolt per second to taken. And then after that, this is MnCO2O4 for figure A. Then sample 1 for nitrogen doped carbon 2, nitrogen doped carbon 1, and sample 3 for nitrogen doped carbon 3. Compared to nitrogen doped carbon 2 have the to measured on more current for around 45 milliamp. Then this overall the structure have to the redox plus EDLC nature. Next one, for electrochemical studies for B value calculation. In the B value calculation, we conform to the for an our supercapacitor figure for nature like EDLC or pseudocapacitor. So here we conform to the for so from that CV we conform to the that B value like slope value to conformed here. So in that B value we conform to the both pseudocapacitor and EDLC nature have. Next, the charge and discharge. The charge and discharge here, the applied current density for around 1 ampere to and 10 ampere per gram. And then overall, then MnCO2O4, the sample 1 and sample 3, the sample 2 have the more discharging time and more specific capacitance. And further, moving to next slide, we show to the specific capacitance table. So then figure in that current density 1 amp the compared to bare and sample 1 and sample 3, the sample 2 have the more specific capacitance. It will have to the good conductivity for around 1200 farad per gram. Next, the comparison table here in previous literature we compared to the for in, our MnCO2O4 material to confirmed here the specific capacitance for in 1 amp 1200, retention percentage for 87%. Next, the specific capacitance of the bar diagram in figure A, the current density versus specific capacitance we showed here. Then the cyclic stability, the cycle stability for 3000 cycle we took. Then the retention percentage compared to the sample 2 have the more retention percentage for around 87%. Next one, electrochemical impedance spectroscopy. Here, the frequency for 1 millihertz to and 10 kilohertz we taken here for low frequency to high frequency. Here, the electrode resistance and capacitance resistance and solution resistance and Warburg resistance, all this resistance we confirmed here. Compared to in MnCO2O4 at nitrogen doped carbon sample 2 have the less resistance. So it will give to the more conductivity. Then the imaginary part of also for around for 48, the real part. So overall, this MnCO2O4 at nitrogen doped carbon 2 have the less resistance. So next, the asymmetric supercapacitor for a 2 electrode system. In figure A, in CV for 5 millivolt per second, here just we compared to the for negative electrode and positive electrode for 5 millivolt per second to measure the current. So the applied potential for around minus 0.12 for 0.55 and for negative electrode for minus 0.12 for minus 0.9. Then figure B is the for same standard but different potential we measured here from CV. So like 1.1 volt to and 1.6 volt. And next, the figure C is the in cyclic voltammetry for the scan rate for up to for 5 to and 100 millivolt per second scan rate. The applied potential for and 1 to for 1.6 volt. And then the figure D have the charge and discharge, the performance for 1 ampere 49 farad per gram. We measured here. Then the Coulombic efficiency for in figure E for 99%, the retention percentage for 96%. Then figure F is the for before cycle and after 5000 cycle we measured on the for impedance spectroscopy. Next, the energy density and power density. In energy density, in previous literature, we compared to the Ragan plot. And the energy density in our two-electrode system for 61, the power density for 2889. Next, the summary of this work. The MnCO2 sphere were synthesized by the solvothermal method. Then the core cell composite to find out to the carbonization method. The crystal structure, morphology, and surface area and composition, oxidation state. All this properties to measured by the XRD and SCM and TEM and BET and XPS analysis. Then MnCO2O4 at nitrogen doped carbon to enhance the electrochemical performance. It will go to the good stability and excellent energy and power density. Next, the chapter 4, the nickel doped cobalt oxide, the spinel nanosphere embedded with the nitrogen doped carbon composite to derived from the bimetallic nickel cobalt metal organic framework as high performance asymmetric supercapacitors. In synthesis procedure, here the nickel doping to change to the three variation like 0.1 mole and 0.3 mole and 0.8 mole. So Then after that, the DMF for using the solvent for 30 ml for trimesic acid and PVP to added to both together to added to stir it up to for 1 hour. After that, in 50 ml autoclave to make the 150 degrees for 6 hours. Then finally, the prepared material to make on 800 degrees for an 2 hour in argon atmosphere. After that, that prepared material to calcinate to the calcination to the 350 degrees for 4 hour. 4 hour. Finally we got nickel doped cobalt oxide with nitrogen doped carbon sphere. In XRD figure A, for in cobalt oxide with nitrogen doped carbon, around the 2 theta value for around for 36, the plane for 311, and compared to sample 2 and 3 have to the slightly the peak intensity to decreasing and slightly the peak slightly the peak shift negligibility is there. And compared to the sample 3 through to increase in the concentration of nickel, so automatically the peak intensity to slightly to increasing. Then the figure B for the FTR spectroscopy, here the stitching and bending vibration to conform to the all this our prepared material to functional group of carbon to hydroxide and carbon to oxygen, all this stitching and bending vibration to conform to the FTIR. So on figure C is the BET analysis in surface area for an 198 m square and gram inverse. The pore size distribution for the 4.85. Next, in morphology analysis, the figure A for the SEM analysis. So figure A is the pure cobalt oxide with nitrogen doped carbon sphere. Then figure B is the nickel doped cobalt oxide with nitrogen doped carbon sphere. For 0.1 mole, this is sample 2 and sample 3. And compared to the sample 3, it was the porous sphere structure for to breaking here, because to increasing the concentration, automatically that particles all the spheres to break it here. And otherwise, all this spheres to uniformly we took on in a SEM analysis and we confirmed. Next one, the TEM and HR TEM analysis. Here, the figure A is the nickel doped cobalt oxide with nitrogen doped carbon sphere, and figure B is the Springer's calculation, the particle size for 0.29 nanometer and 0.24 nanometer. Next, the elemental mapping to conform to the nickel and cobalt and carbon, nitrogen and oxygen, all this element to conform to the elemental mapping. Next, the XPS spectroscopy. In that XPS spectroscopy, we conform to the all this element like nickel and cobalt and oxygen and carbon and nitrogen oneness. The figure A is the for survey spectroscopy we confirmed here. So for nickel 2p, the valence state for around for 1/2 and 3/2. Then the cobalt 2p, and then the carbon oneness and the oxygen oneness and nitrogen oneness, all this element to conform to the XPS spectroscopy and the composition to finally to confirmed here. Next, the electrochemical studies of in CV, cyclic voltammetry. Here in that CV for in 3 electrode system, they applied standard for up to for 5 millivolt per second to 100 millivolt per second. They applied potential for 0 and 0.55. So compared to for cobalt oxide with nitrogen doped carbon and this nitrogen doped nickel doped nitrogen doped carbon sample 1 and sample 3, that sample 2 have the more to measure and the more current for around 65. So overall, this is how to the for an redox with EDLC nature and to the in CV structure. Next one, the B value calculation. In the B value calculation, from that CV we confirm to the for pseudocapacitor nature like EDLC or pseudocapacitor. Here we confirm to the both pseudocapacitor plus EDLC to confirm on B value from that B value calculation. Next one, the charge and discharge with the specific capacitance plot. So here figure A is the cobalt oxide with nitrogen doped carbon and sample 1 and sample 2 and sample 3 to charge and discharge we measured here up to for only to 1 amp. So when compared to that sample 2 have the more discharge, it will go to the more performance. Then the figure B and figure C, all this figure to measure to the for around for 1 ampere current density to then up to for 10 ampere per gram to current density. to applied potential for 0 to 0.55. So compared to the sample 2 have to the more discharge time. Then figure F is the current density versus specific capacitance plot. Then this is the specific capacitance table. So compared to all the sample, in sample 2 have the 1284 farad per gram from 1 ampere. Next, the previous literature we compared to the our prepared BTC derived nickel cobalt oxide with nitrogen doped carbon. Sample 2 have to the specific capacitance for 1284 95% for attention percentage. Next, the cyclic stability. Here we the cycle we taken to the for up to for 3000 cycle. For retention percentage for in sample 2 have the 97% compared to other sample, it will go to the more retention percentage. Next, the impedance, the before cycle and after 3000 cycle, we measured on the impedance up to the frequency range for 1 millihertz to under 10 kilohertz. So overall, that sample 2 have the less resistance because it was due to the more conductivity compared to other impedance to other sample. So next one, the asymmetric supercapacitor. Here, the nitro electrode we choose to the multiple carbon nanotube for choosing to purchase it on commercially. Next one, the nickel cobalt oxide with for nitrogen doped carbon sphere for sample 2 for up to for CV structure for 0 to 0.55. The multiple carbon nanotube for choosing the nitro potential for minus 0.12 for minus 0.9. So next the figure B, here same scan rate with a different potential we measured on in CV for a two electrical system, and figure C for same current density but different potential we measured for an charge discharge here, and figure D for up to for 5 to and 200 millivolt per second to different scan rate we applied here, and the potential for 0 to up to for 1.5 to applied potential in current density for 1 ampere to 10 ampere per gram to measured. So next the figure F is the specific capacitance and then current density. Overall around for 1 ampere and 2 electric system for 85 for the specific capacitance. Next one, the figure A is the for an capacitance retention for an 2 electron 92%, the Coulombic efficiency for 98%, and overall the cycle number of cycle we measured on 3000 cycle. Figure B is the for before cycle stability and after cycle stability to measure on the CV. So before cycle stability, it was measured on around for 0.9 for current to measure on current. So after stability slightly to decreasing. So like that the charge discharge also to measure on before cycle stability and after cycle stability. Next one, for impedance spectroscopy for before cycle and after 3000 cycle, we measured for the impedance spectroscopy. So the energy and power density, the energy density for compared to the in previous literature. So in the nickel doped cobalt oxide with nitrogen doped carbon sphere with multiple carbon nanotube, the energy density for 26, the power density for 416. Next, the summary of this work: this cobalt oxide and nitrogen doped carbon sphere and nickel doped cobalt oxide and nitrogen carbon sphere to synthesis by the carbonization method, and the elemental composition and the structural characterization we confirm to this and XPS and SEM and TEM analysis. Then this sample it will go to the expect good electrochemical performance and the synergetic interactions of two electrode system to generate the more active site and to respond for the enhanced the supercapacitor performance, and consider the environmental friendly and low cost and the efficient catalyst for a supercapacitor. Then chapter 5, the enhanced electrochemical performance of cobalt doped MOS2 with NSRGO composite as electrode material for supercapacitor application. The synthesis procedure we prepared to the hydrothermal method for using these precursors sodium molybdate and thioestimate and cobalt nitrate and GO. Then after that to make the 200 degrees for 24 hours, then finally to dry to oven, and then we got the cobalt doped MOS2 with the NSRGO composite for nanosys seed structure we confirmed. And figure A for the next XR XRD for MOS2 for the intensity for around 10.1, the plane is 002. Then cobalt doped MOS2 for compared to MOS2, slightly the peak intensity to decreasing and slight shift is there. Next, after that composite of NSRGO, here the peak slightly to peak intensity decreasing and peak shift is present compared to pure and doping. Then figure B is the TEM and TEM analysis. Here the slightly to agglomerate to the nanosheet. Then figure C is the to measure the interplanar distance for around 0.49 nanometer for particle size. The plane is 002. Next, XPS analysis. Here we confirm to the for molybdenum and cobalt and sulfur and nitrogen and carbon and oxygen oneness, all this element to confirm from that XPS. Then there are cyclic voltammetry. Figure A for the figure A for MOS2. So here the applied scan rate for up to 5 to 100 millivolt per second, and figure B is the cobalt doped MOS2, and figure C is the cobalt doped MOS2 with NSRGO composite. So compared to in figure C, it will give measured on the around 33 for current to measured here. So next one, the charge and discharge. Here compared to pure and doping, the composite it will give to the more discharging and it will give to the more specific capacitance. And moving to next slide, I'm just showed here. So the current density for 1 amp around 626 per farad per gram. Next, the cyclic stability of cyclic stability, then specific capacitance for bar diagram, the current density versus specific capacitance. Is around the cycle stability for cycles for we measured on 4000 cycle. The retention percentage of our composite material 95%. Next, the summary of this work, the nanosheet of MOS2 was synthesized for using the hydrothermal method. The cobalt doping leads to highest supercapacitor performance, not only to the individual counter but also to other composition also to play to improve the performance. Then the improved the performance for a composite ascribed to the synergetic effect, the cobalt doping that create the more active site and through the formation of defect. So next, the chapter 6, the nanoflower nickel cobalt LTH nanosheets coupled with the NSRGO composite as electrode material for high performance asymmetric supercapacitor application. The synthesis procedure here, the nickel and cobalt precursors we taken to the 1:2 ratio, and the C-tab here we used here. So to overall this synthesis method to prepare the solvothermal method, then 180 degrees for 24 hour to make the in oven. So finally that prepared material to make the composition of NSRGO for 10 and 20 and 30. Like that, three variation we prepared here. Finally, we got the nanoflower coupled with the NSRGO composite. So in XRD for a nickel cobalt LDH for an around for 2 theta value for 10.1, the plane is 002, and the composition of NSRGO sample 1 and sample 2 and sample 3, the peak slightly to intensity peak is decreasing and slight negligible peak shift is there. Then the NSRGO peak for 2 theta value around for 22 for 002 plane, and the GO peak for around 10.1, the plane is 001. So here that NSRGO, the NSRGO peak is not showed here. So further analysis we confirm to the Raman analysis. So the Raman shift for a nickel cobalt oxide, nickel cobalt layer double layer hydroxide, so around 500. And sample 1, so slightly the peak intensity to shift is there. Then the sample 2 have the for NSRGO confirmation, the D and the G band is to present here. So the value for 1.2, then sample 3 for ID divided by IG value is equal to 1, so 1.0. Then the pure NSRGO have to the 1, then GO have to the 0.93. Slightly the peak intensity shift is present. So the SEM and HRTEM analysis, the figure A is the pure nickel cobalt LTH for an SEM analysis. Here the flower-like morphology to nano flower-like morphology to confirm here. Figure B is the TEM analysis to layer and double layer hydroxide to conform to the pure nickel cobalt ligate. And figure C is the for SEM analysis of our composite material. Here we one more time that nickel cobalt ligate to composite to the NSRGO flower-like morphology to conform to the figure C and D. So the figure is the pure NSRGO for a nanosheet morphology to measure on here. The particle size for to conform to the Springer's calculation for 0.26 nanometer. The plane is 002 and 0.25 nanometer and 0.23 nanometer to conform to the for nickel cobalt LDH with the NSRGO sample 2. Then the elemental mapping of nickel and cobalt and oxygen and nitrogen and sulfur and carbon, all this element to conform to the in HRTM analysis. Next, the XPS. Here the XPS to conform to the for in figure A for in survey spectroscopy for sulfur, carbon and nitrogen, oxygen, cobalt and nickel, all this element to conform to the survey spectroscopy. So figure B is the nickel 2p and figure C is the cobalt and figure D is the oxygen. Then figure E is the carbon and figure F is the nitrogen, figure G is the sulfur. So all these elements we confirmed here. Next, the CV. In CV, we applied potential for up to 5 to 100 millivolt per second. The potential range for and 0 to 0.63 from that CV, and compared to the sample to measure on the more current for around 50. So it will go to the more acceleration and reduction peak area. So to compare to all this element, all this sample. So next the B value here we confirm to the both redox and EDLC nature to conform to the all this figure from that CV. In the B value we confirmed here. Next, the charge and discharge, the current density for up to for 1 ampere to 10 ampere per gram we measured here. And overall, the sample 2 have the more discharging time. It will go to the more performance compared to other sample. So the performance for an sample 2 for the 3,309 farad per gram for 1 ampere per gram for current density, and sample compared to other sample, it will give to the more performance. Next, the previous literature we compared to the our nickel copper LDH for NSRGO composite for 1 ampere 3,309 for 88% of retention percentage. Next, the specific capacitance of bar diagram, the current density versus specific capacitance just to be showed here. The cyclic stability for 5,000 cycle we measured. So the retention percentage for overall the sample 2 have the 88%. Next, the asymmetric supercapacitor for 2 electrode system for activated carbon with nickel cobalt LDH with the composite to the NSRGO sample 2. So my we measured to the CV for 5 millivolt per second to given to the comparison. So the next figure B, same scan rate with the different potential we measured on the CV to 2 electrode system. Then same current density with the different potential for charge and discharge we measured in figure C. Then figure D is the for cyclic colorimetry up to 5 to 100 millivolt per second to different scan rate. The potential for 0 to 1.6 we measured here. Next one, the charge and discharge, the current density for 1 ampere around 163 farad per gram. We got to the result and the performance. Then the cycle the cyclic stability for 10,000 cycle we measured here. The retention percentage for 89%. So in 2 electrode system. Next, the energy and power density just we compared to the in previous literature. So in energy density, our prepared material for 116, the power density for 1,606. Next, summary and future work. In summary, in overall for MnCO2O4 with nitrogen doped carbon, nickel doped cobalt oxide, nitrogen doped carbon, and nickel cobalt LDH composite to NSRGO. Here it will give to the for a nickel cobalt LDH, it will go to the more performance compared to other. It will go to the more energy density for 160 and the power density also 1,606. So the specific capacitance in 2 electrode system for 163 and the capacitance retention for 89%. Next, the future work, the nickel cobalt oxide with the halosphere, then composite to the NSRGO will be prepared on hydrothermal or solvothermal method. Next, the MnCO2 for oxygen vacancy with oxygen vacancy we want to prepare, and different nanostructure we want to try. So next, list of publication. Next, my conference and workshop and seminar presented and attended. Acknowledgement. I thank for Dr.Maiyalagan, Associate Professor and Research Supervisor and Department of Chemistry. And I thank for Professor C. Muthamil Chelvan, Vice Chancellor and SRMAST. And I thank for B. Napoleon, Dean Research and SRMAST. And I thank for D. John Thiruvadigal, Chairperson, School of Applied Science. And I thank for Professor M. Arthanariswari, HOD and Department of Chemistry. And I would like to thank for Dr. A. Stephen, Professor and Department of Nuclear Physics and University of Madras. And I would like to thank for Dr. A. K. Sahu, Senior Scientist, CSIR Sikri, Madras Unit, and Taramani. And I thank for Dr. B. Ganesh, Senior Principal Scientist, CSIR Sikri and Karakudi. And I would like to thank for my family and colleagues and friends. Thank you, sir. Thank you to all of you, sir.
Sir, Stephen, sir.
Yes.
Comments, sir.
What about others? Others is not here.
Salvo, he said he will give some comments actually.
Right. So anyway, the presentation is good. Let me congratulate the candidate as well as his guide. So I have a few general questions.
Yes,
You have discussed about XRD and other things. You never inform about the crystal structure of each system. You have simply shown the XRD pattern.
Yes, sir. Yes, sir. Cubic phase structure, sir.
You go to MnCO2.
Okay.
So what is the structure?
Sir, cubic phase, sir, octocapsular structure is there, sir. From MnCO2O4 for cubic phase.
Oh, it's a phase center cubic or a body center cubic?
Sir,
anyway, you check it out because you simply have given XRD pattern. Okay.
Okay, sir. Okay, sir.
Because MnCO2O4.
So AB2O4, spinel structure.
Spinel structure.
AB2O4.
Right. So at least you should know which system is in which crystal structure. And,
Okay,
and you have done it's a doping or substitution. And
sir,
wait. What do you mean by substitution? And what do you mean by doping?
Sir, doping means to low, for example, nickel doped cobalt oxide. Here, that low concentration of precursors we want to.
Now, what is the quantity? Low concentration means how much?
0.1 mole and so 0.3 mole.
No, 0.3 mole, 2 mole is in the precursor level. I am just talking about in terms of how much you are going to dope instead of Mn or cobalt. Whatever system no, you have doping means. What is the percentage? Why I have a little bit doubt whether it is a dope system or substituting with other. It is not clear about.
Okay, sir. So here I'm this nitrogen doped carbon. How I want to compose it means just the dopamine derived to nitrogen doped carbon, sir. So in pure MnCO2 for first
Wait.
preparation.
See, let me
Go to nickel cobalt oxide, nickel doped cobalt oxide.
சிலம்பரசன் நான் என்ன
Yes, sir.
கேக்குறேங்கிறத கொஸ்டினை கவனிங்க. I am just simply asking. It's a very simple question. Whether you have understood or not. What do you mean by substitution and what do you mean by doping? If you are doing doping, okay. Which atom you have doped in your system? Okay. Don't confuse with composite and other thing. I'm simply asking a simple question, right?
Okay, sir.
Suppose it is less than 2%, you cannot see the doping level in the XRD pattern. That's why I'm asking. You said it's a doping system. So doping or substitution?
So this MnCO2 is a doping or substitution?
So doping.
Syllabus, nothing to worry. You just go back to your system. Okay, whether it is in the doping or in the substitution. These are all some very fundamental questions. And another question, maybe you show some EDAX spectrum. Show me some EDAX. Elemental analysis, or you go to elemental analysis. Yes, fine. Here it is 500 nanometer. The spheres are 500 nanometer.
Yes, sir.
Okay. And what you are trying to establish is cobalt or carbon or nitrogen within the sphere.
Yes. Yes.
Sphere size is 500 nanometer. Am I correct?
Okay, sir. Yes, sir.
Now you try to establish each dot is a one atom. Is it not?
Yes, sir.
Okay. My simple question is, each atom is something around, what is the dimension of atom? It is 0.1 nanometer or 0.2 nanometer. Definitely less than a nanometer. Correct?
So definitely, yes, sir, less than nanometer only.
That's why I have a little bit doubt. You have to clarify. What you have shown is a single atom. It's an agglomeration of atoms. Because each dot, because the ball is 500 nanometer size, and few dots you have shown, it's a cobalt or carbon, whatever. My simple question is, even the nitrogen thing, you have shown few dots. Whether each dot is less than 0.1 nanometer, less than 0.1 or 0.2 nanometer means maybe we can take it as an atom. Okay.
Okay, sir.
So I have a little bit doubt or confusion. You have to clarify.
Sir, here, yes, sir, I understand, sir, that question, but the particle size is compared to this 500 nanometer, it was less than only, sir.
No.
Yeah,
No. 500 nanometers a particle size. That I can understand. You try to establish each dot is a one atom.
Sir, that one.
Each atom is one atom. Each dot is one atom. Is it possible to see 0.1 nanometer or 0.2 nanometer in the scale of 500 nanometer? That's why I ask, my simple question is a single atom or an agglomeration of atoms.
Atom size, exactly. Sorry, sir.
No. Don't say sorry. Whether it is single atom or agglomeration of atoms. Because the 500 nanometers is a cluster or whatever slide size or grain size, whatever. Each ball is one slide, okay, or one particle. That is your claim. Is it not?
Yes, sir.
In that case, the each dot, it cannot, I mean, yeah, you can't measure less than a nanometer. It's like a 0.1 nanometer or 0.2 nanometer. Okay.
Yes, sir.
Another question, in most of the TEM or HR TEM image or EPSEM images, not only you, most of the people try to give a flower-like morphology or symmetry. There are a lot of symmetry in the nanometer scale.
Yes, sir.
Flower-like structure. Yes, exactly. Really interesting, fantastic morphology. Why in lower dimension, the atoms are trying to mimic the symmetry? Is there any reason? Not only
Sir,
you, everybody is climbing flower-like structure or cauliflower-like structure or needle-like structure. Then you have a branches. There is always a symmetry. What is the reason for this symmetry at the lower dimension? Anyway, these are my observation. Maybe you try to find the answer.
okay, sir.
Okay, that is good for you as well as we people, right? Why
Okay,
there is
sir.
always it forms a symmetry at the lower dimension.
Okay, sir.
Even if you see your own results, no, there are a lot of symmetry. What is the reason for symmetry in the lower dimension? Right, that's all. Okay. Okay, Maiyalagan, that is all my questions.
So what about the title and all? Is it okay, sir? Go to the
You
title.
just go back to the title. Transition metal based. Still heteroatom doped carbon. Are you going to dope carbon in the metal side?
Sir, heteroatoms. Atoms means that nitrogen doped nitrogen and that boron, phosphorus.
இல்ல Maiyalagan,
So nitrogen to heteroatom doped carbon, sir, and he is using all transition metal. Go to that. Go to that chapter. No, the other one. You saw not that.
nitrogen, wait, nitrogen doped
Chapter 3, 4.
porous carbon. So you are trying to dope nitrogen into carbon.
Previous. Chapter 2, chapter 3, objective, somebody.
இல்ல nitrogen doped.
Before that. This one. This is the chapter 3, MnCO2 4 at nitrogen doped carbon. Chapter 4, nickel doped.
இல்ல. My question is, are you going to dope nitrogen into carbon side?
Yeah, nitrogen doped in the carbon side.
And this is no way connected to your metal oxide side.
No, we are connected to metal oxide.
Okay. Then you can give it this way, no? Nitrogen doped carbon based metal oxides.
Okay.
Nitrogen doped carbon metal oxide composites.
Some case he has put sulfur also, nitrogen with sulfur. That's why I put that.
No, you just reform it. Nitrogen doped carbon metal oxide composites for high performance supercapacitors. You want to say supercapacitor or power density materials or what do you call it? Energy materials. I didn't follow all the thing. You have given supercapacitor measurements in all the chapters.
Yeah, all supercapacitors.
Yeah, you have come back.
All are supercapacitors.
All are supercapacitors. Then okay. Then you can put high performance supercapacitors. So carbon doped
Okay, sir.
carbon doped metal oxide. Metal oxide, hydrogen. Sorry, hydrogen. Sorry, hydrogen doped metal oxide composites for high performance supercapacitors.
Okay, sir.
Okay, you fine tune further if you want.
Okay, sir. Thank you, sir. Thank you. Thanks for coming to the meeting, sir. And Sagu has sent us some comments in the things. I will give it the
Okay.
comments to you.
Okay, thank you. Okay.
Thank you so much, sir. Sorry for the delay, actually. Sorry,
Okay.
sir.
Thank you, sir. Thank you, sir.
Sagu, thanks for joining the meeting. Send me the comments. Thank you.
Thank you, sir.